In the Unit 6 discussion, Michael asked how you do homework problem number 10. Homework problem 10 involves a diver who jumps off a diving board into the water and then comes to a stop at a certain depth below the water. The reason why the diver stops is because there's a resistive force, not air resistance, but water resistance. And the question is, how strong is that water resistance force? What is the value of that force? And I'll use this label R for resistive force. It's a common thing to use. Now we can set up this problem using conservation of energy with non-conservative forces. A resistive force like air resistance or friction or water resistance is a non-conservative force. So our conservation of energy equation looks like initial potential energy plus initial kinetic energy plus the work done by the non-conservative force, by this water resistance, equals final potential energy plus final kinetic energy. Now in this problem, our conservation of energy equation simplifies quite a bit because the diver starts from rest and ends at rest. So there's no kinetic energy in the initial situation, the diver standing still. There's no kinetic energy in the final situation. The diver has stopped at the maximum depth. So we just need to worry about three things. The initial potential energy is just mg times the initial height, which I'll call h. I labeled it h on this diagram. And the final potential energy is mg times the final height. And there's one thing that's a little bit subtle here. If we say that water level is 0 height, then the diver finishes below 0. So this final height, since it's below 0, I'll write negative d. That distance d, but below 0. And one more thing to put in there, it's the work done by the non-conservative force. And whenever you have a non-conservative force doing work, it's negative. Non-conservative forces always tend to slow the system down. That means they do negative work. Another way to think about that is when the diver enters the water, the displacement vector points down. Resistive forces always oppose the motion, so the water resistance force will be pushing upward. Those two vectors are in opposite directions. So by the definition of work, where there's cosine of that angle, that's cosine of 180, which is negative 1. So this is going to be a negative number, and by the definition of work, force times displacement times cosine of the angle, that'll be force times the displacement. Keep in mind, the resistive force, the water resistance, only occurs when the diver's underwater. So the displacement distance is d, the underwater distance. We don't include h in there because that's when the diver's in the air, and that's not water resistance. That would be air resistance if we were accounting for that, but we're ignoring air resistance in this problem. So that's the complete setup. And we do a tiny bit of algebra and we can solve for R. We move things around and can distribute this mg and lastly divide both sides by d. And the water resistance force will be mg times h plus d over d. That's it.